Now, sometimes you'll have sets that don't have an intersection. If they don't have an intersection, we say that they are disjoint. So if I come up with two new sets, let's say C, which is equal to numbers less than 2, and let's say D is equal to numbers greater than 2. Since we have these words here, I would like to try and write them into set notation. So if we're talking about numbers less than 2, we're still referring to the same sample space, which contains the numbers 1, 2, 3, 4, and 5. So the numbers that are less than 2, that's actually just the number 1. Greater than 2, we're talking about 3, 4, and 5. If you look at these lists, you can see that they have no elements in common. So if I'm looking at the Venn diagram, I could talk about, well, here's C with element 1 in it, but this time they would not touch each other because they don't have any overlap. D is 3, 4, and 5, and the leftover, I have 2 sitting there. So since there is no intersection, no overlap, we say they're disjoint. And what we'll write is C intersects D. They have no elements in there, so if I want to write a set, I just draw a set that has nothing in it because they have no elements in common. Sometimes we'll write this notation, which is another way to also refer to this set that's empty. Now our last operation is the complement. Now when we say complement, we're talking about all elements in sample space that are not in the set we're talking about. So if we're talking about the complement of A, we're talking about all elements in the sample space that are not in set A. And our notation for that, we write A bar. So this means complement. So if we look back, A was equal to the set that includes the elements 1 and 2. So if we're looking at our sample space also, rewrite that here, 1, 2, 3, 4, 5. When we say complement, we're looking at all the numbers in our sample space that are not in A. So in our sample space, 1's in A, 2's in A, but 3, 4, and 5 are not. So that means 3, 4, and 5 are in our complement. Picture-wise, I could draw another Venn diagram. If we see A is 1 and 2, then all the other numbers, 3, 4, 5, remember that inside our rectangle should be our entire sample space, which it is here. So A is 1, 2. The complement of A would be everything else outside of A, not including A. One other place that you'll see complements is looking at complements of inequalities. So what we mean by that is if you're looking at the numbers x such that they are larger than 1, what we're talking about on a number line is looking at 1, not including 1, and everything larger, we continue going to the right. So to show that it's going to continue in the right, I'll draw a little arrow on my shaded piece here. So this is the set of all numbers that are greater than 1. So if I'm looking at the complement, if I'm looking at the complement of this set, I want all those things that are not on this number line here, but that make up the rest of the number line. So that would mean we're going to talk about actually including 1, and instead of greater, we want everything less than. This would be the complement of x greater than 1. So in other words, we'll write x is less than or equal to 1 is the complement of x greater than 1. We can also use interval notation to talk about the complement. So if we're looking at our picture again, we were at 1. We have x greater than 1 here. And we have x is less than or equal to 1. For interval notation, we always want to talk about endpoints. So we're talking about writing x is less than or equal to 1 in interval notation. You look at it and you don't have 2 endpoints. On the left, this arrow signals that it's going to go forever to the left, which is going to go to all the negative values. So we can write negative infinity. And since infinity, we're going to keep going forever, it's never going to really touch there, we're going to draw a parenthesis to show that. But we do have one endpoint there. We have a 1, and it does include 1. So this is the interval notation for the complement. And we could try that one more time. Let's consider the inequality negative 3 is less than or equal to x is less than negative 1. Again, I want to see the picture of this. So I'm going to put in some values here. Okay, so what we're talking about first is the set of all numbers that are less than negative 1, so they don't include negative 1. And at the same time, these numbers here, it opens to what's bigger, so it's greater than negative 3, and actually could equal negative 3. So we're talking about all the elements in here. So now if we want the complement of this, well, we don't want to be in here anywhere. So we could actually be touching negative 1 and getting everything larger. At the same time, we can't be negative 3, but we could be everything smaller. So this right here is a picture of our complement, those two little segments. So for the very first segment, so again, we don't have the endpoint, but that's going to go to negative infinity, and then to negative 3, and not including negative 3. And then we also have this little segment, which will be from negative 1, that's the one endpoint, and we'll include it. And it will go forever to the right, which gets bigger and bigger and bigger positive numbers, so we'll say to positive infinity. And so we're saying both of these sets, so the complement is going to be these two things. So I could say that you're either in negative infinity, negative 3, or you're in negative 1 to infinity, and we separate those by using our union symbol. So this is our complement. Now let's look at try this. If we have that A is equal to the set that includes the number 7, 8, and 9. B is equal to the set that includes 8, 9, and 10. What is this set?